Welcome to 34th lecture for the NPTEL course on computer system optimization for machine learning. We will continue on distributed service and then we will start on fault tolerance in machine learning. Okay. So, in the last lecture we discussed about the different characteristics between prefill and decode. Okay. So, we discussed that we can throw more GPU if the service level objectives are not met. If we throw more GPU, then of course we will have good user experience. The user will be happy because all the service level objectives are met, but with higher cost, right. So, we have to make sure that again higher cost doesn't necessarily mean that we will have good performance or we will have equally good performance. If we throw 4 GPU versus 1 GPU, we should be expecting like 4 times throughput, correct. Let us see whether we can do that or not. Again we can do co-location, like whenever we have multiple GPUs we can do co-location, we can do some coupled parallelism. For example, for prefill we can probably do tensor parallelism, we can chunk the prefill, or we can like prefill is compute intensive, right. We can break the prefill into multiple portion and then different GPU can execute those portions, but prefill is not very good for pipeline parallelism. Decode is good for pipeline parallelism, but then during decode, decode is less arithmetic intensive, right. The arithmetic intensity of decode is less, so tensor parallelism is probably not so good for decode. We don't need to, we have barely any chance to segment the decode computation and map it onto different GPUs, right. So, is there a better way to achieve better good put per GPU? Again, if you remember, good put is nothing but how many requests per second actually met the service level objective. So, throughput is how many requests per second is served, but then not all requests which are getting served may satisfy the service level objective, right. So, the requests which are meeting the service level objective are part of good put. Okay. So, let us go back and then let us again discuss how this prompt computation versus token generation happen, right. So, let us say we have a user prompt where we have this prompt which is better, pizza or burger. Okay. You might have different opinion, but in this lecture we will say that pizza is better. Okay. Now, the user prompt is which is better, pizza or burger, that is the prompt, that is the prefill phase, and during prefill phase it just generates one token. After that other tokens will be generated sequentially, right. So, as we already discussed many times that the prompt phase or the prefill phase is compute intensive. Not only compute intensive, it requires lot of power. So, remember, more compute is equivalent to more power. It might not scale linearly, like 2x more compute may not be 2x more power, it may be even higher. Okay. And there is limited batching benefit. As we already saw that the batching, like if the y axis is the throughput and then the x axis is the batch size, we saw the curve is mostly like this during prefill, right. That means since it is compute intensive, since prefill is compute intensive, even if we put more batches or even if we club more requests in one batch, we might not get higher performance because prefill is already compute intensive. If the batch size is more, it will our GPU will end up oversubscribing, and then the end result will be like not so high throughput, right. So, limited batching benefits during prefill. On the other hand, the token phase or decode phase, again prompt phase is nothing but prefill and the token phase is nothing but the decode. Okay, there can be different names, right. During the decode phase, the thing is memory intensive. Why memory intensive? Because remember, we have to fetch the KV cache, yes, along with all the weights, right. So, all the weights were anyway getting fetched during the prefill, but on top of the weights during decode we have to fetch the KV cache. So, it is memory intensive, and we have seen that batching improves the throughput. Why? Because during decode, if you are using KV cache, all the QKV matrix sizes are 1 by D. So, if we that means the arithmetic intensity is low, right? The computation, the amount of computation during the decode is low. So we can club many computation or computation from multiple requests. Therefore, we can have batching so that the throughput increases, right? So that's the difference between prefill and decode, or let's say prompt phase and the token phase. Okay. Now, if we execute both the prefill phase and the decode phase like on the same hardware, that's inefficient. Okay. So, in this particular figure you can see that we have one server where we are executing both the prefill and the decode. Okay. That's inefficient because I mean, of course, we can do some Sarthi like batching, but still we can see that there are some drawbacks of Sarthi, right. So, instead we can actually split the phases on different servers. Okay. So, there are techniques splitwise and DistServe. These are again papers which you can go over. Those techniques split phases onto different servers, right. So, for an example, we can have one prompt server, we can have another token server. In prompt server, we can have smaller batches, maximum power. In the token server, we can have large batches and power can be capped. Okay. Now, one thing is yes, that is fine. We can have this prompt server and token server, but how about KV cache? So, remember the KV cache is first generated by the prefill and that gets used by the decode again and again, right. Of course, during decode the KV cache size becomes larger and larger, but if we have two different server, how the KV cache will be translated, right. So, each phase could use the preferred hardware and then the KV cache has to be communicated from the prompt server to the token server. Okay. So, we can have one prompt GPUs and we can have token GPUs. Whenever the prompt server finishes this execution of this prefill, then the KV cache can be transferred to the token server, right. So, let us say there is some GPU input buffer, so that GPU input buffer can take the KV cache from the prompt server to the token server. So, splitwise, this splitwise is a technique. Again, I know you know this splitwise is an app where I do not know whether you use this app or not. It is very useful for this splitting the expenses among your friends. Anyway, the splitwise here is a paper which uses GPU InfiniBand to shift the states. When we say state, that is nothing but this KV cache. Okay. So, the KV cache has to be shipped from the prompt GPU to the token GPU, so that the token GPUs can execute this the decode phase, right. Now, this transfer can be parallelized for high bandwidth. Let us say the total bandwidth is 100 Gbps and then let us say we have 4 GPUs in each of the server. So, each of the GPU can transfer the KV cache parallelly to each other server in the GPU. So, let us say each GPU bandwidth is 25 Gbps, that is why we get the total bandwidth is 100 Gbps. Okay. So, we can parallelize this transfer. So, remember whenever we say server, one server may have multiple GPUs. Okay. So, if there are multiple GPUs, then the KV cache might be distributed. So, let us say in this particular case each GPU holds 1/4 of the KV cache. Now, if each GPU bandwidth is 25 Gbps, 25 GB per second, and then if we parallelize the transfer of the KV cache from this prompt server to the token server, then the total effective bandwidth is 25 multiplied by 4, which is nothing but 100 Gbps. Okay. So, we are assuming 4-way tensor parallelism in this case, correct. Now, still I mean with parallel communication or the parallel transfer, we may reduce the transfer time, but still the transfer overhead might be large, right. So, in this particular timing diagram, it is exactly shown the same thing. We have this prompt server where it computes the prefill prompt phase and then there is a transfer state. So, during this transfer state, the KV cache is being transferred from the prompt server to the token server, or the prefill phase to the decode phase, right. Now, once the whole transfer is over, then only the token server or the token phase will start, the decode will start, right. And this KV cache size can be of hundreds of GBs. We already have seen some example where we have seen that KV cache is can be obtained from the sequence length, D model, etc., etc. And if the model size is high, if the hidden dimension is high, then the KV cache size is also high, right? Is also very, very high. Now, in this token server, I mean, again, there is a prompt phase in the prompt server, and then the KV cache needs to be transferred from the prompt server to the token server. Okay, so this transfer state can be like very, very high, and this adds to the latency, right? Nothing is free. Everything, every operation in our system takes some time. Every memory operation takes some time, right? So, in this case, if we talk about the time to first token TTFT, this TTFT will be prompt phase plus this transfer phase, right, which is actually high, correct. Now, how to reduce this transfer state? So, this what we can do is we can start shipping the KV cache after the first prompt layer, right. So, remember, all these LLMs have decoders, and then they have like multiple of decoder layers, right, correct. So, and each decoder layer gives one KV cache, correct. So, let us say this is KV1, KV2, KV3, etc. Okay, the people who studied in KV now will enjoy this. So, we can start shipping the KV cache after the first prompt layer. So, let us say this first decoder layer or the first layer got executed, it will generate the KV1, right, the first KV1. So, each layer will have their own KV cache. So, whenever the first layer of KV cache is or the first layer of the transformer model gets executed, it will generate the KV cache for the first layer. Okay. Now, this KV cache of first layer is independent of any other KV cache, correct. I mean, during prompt we do not need this KV cache. So, as soon as the first layer gets executed, as soon as the KV cache of the first layer got generated, we can start shipping, right. So, we do not need to wait for, let us say there are 12 layers of this transformer model. We do not need to wait till this KV cache for the 12th layer is generated, right. Once the KV cache for the first layer is generated, then we can start shipping the KV cache, right. So, that is why you can see that the transfer delay, the transfer state and the prompt phase, the transfer state and the prompt phase can be overlapped, right. So, that means whenever this KV cache of the first layer is getting shipped to the decode or to the token phase or to the token server, at the same time the other layers computation can happen, right. So, that is why we can overlap this prompt phase and the transfer state. So, at the end you can see that the delay is very less, right, we are reducing the delay. So, the earlier if we do not do this overlap, the entire transfer state was adding the latency of entire transfer state was adding to the delay of the request or time to first token of the request, but now we reduce this delay, right. So, that is how splitwise this particular technique overlaps the transfer with the prompt phase, right. Now, let us see, now so far what we have seen that like decode and prefill has totally two different characteristics. Decode is memory bound, prefill is compute bound. So, if we actually execute prefill and decode on the same server, then we may not be able to get good performance benefit, right. So, that is why we are disaggregating the server, that is the distributed service. We are disaggregating the server or we are distributing the what should I say, computation. Now we can have one prefill server, one decode server or one token server and another prompt server. Now, of course, that will we will see that whether now it is time to see the result. We will see whether that disaggregation achieves better good put or not. Okay. Now, in the first result, we can see that co-location, I mean one GPU for both prefill and decode, we are co-locating prefill and decode in one GPU. You can see that this is the TTFT, time to first token. So the x axis is request per second and the y axis is time to first token. Okay. So you can see the P90 means the P90 TTFT is less than 400 millisecond. That means the 90% of the tokens or 90% of the request has TTFT of less than 400 milliseconds. So I think one is for prefill and another is for decode, and for the decode, yeah, this is the prefill, and the rate at which the prefill is served is 3 requests per second. Okay. Now the rate at which the decode is served is 1.6 requests per second. I mean, this is the optimal point that they are showing. Okay. Again, not optimal point, sorry, the 90% of the token has prefill of, I mean, if we take this TTFT as 400 millisecond, then we will have the prefill of 3 RPS, 3 requests per second. Okay. Now, maximum system good put is nothing but minimum of prefill and decode, which is nothing but 1.6 request per second per GPU. Okay. So that means if we have just one GPU, it can sustain just 1.6 request per second, which is very less, right? And I think I am not sure, I have not shown you which GPU they are using, but it's easily be like 800 GPU. Now let's see, when we disaggregate, let's say we have two GPUs for prefill and one GPU for decode, you can see that prefill has now the throughput of prefill is now 5.6 requests per second, and the throughput of decode is 10 requests per second, right? Now, because since we have disaggregated, right, we have disaggregated this prefill computation and decode computation into two different servers, right? So if we do that, then you can see that you can increase the prefill throughput. Now remember, this prefill throughput is per GPU, right? So that means if we have 3 GPUs, or if we are having 2 GPUs for prefill, then the disaggregation good put is minimum of 5.6 multiplied by 2 and 10, right? This 10 is for decode. Again, this will bottleneck the request per second, the good put, right? Remember, when we say good put, we mean the request which actually satisfies the service level objective. Not all requests may satisfy the service level objective. Some requests may have higher time between token or time to first token. Okay. So as you can see, in this case we have the disaggregated good put, means if we disaggregate the computation between a prefill server and the decode server, or prompt server and a token server, you can see the disaggregated good put is better. So that is this good put is minimum of 5.6 multiplied by 2. Why multiplied by 2? Because we have 2 GPUs for the prefill, right? Comma 10. So the decode has good put of 10 requests per second divided by 3 GPU, because we want to see the good put per GPU. So this will give us 3.3 requests per second per GPU. Now see here what we actually did. So remember, we threw more GPUs. So this has just 1 GPU and this experiment has 3 GPU. Of course 3 GPU, and then service was distributed, right? We put more GPUs in action, but in return we got more throughput per GPU, right? So here per GPU the throughput was 1.6 request per second. Here we actually doubled the throughput per GPU, and that's where you have good ROI, you have good return on investment. So you invested thrice, but then the return is 6 times, right? So Why return is 6 times? 3.3 request per second per GPU. That means our total throughput will be around like 10 requests per second, right? That's a total throughput, correct? So we invested thrice from 1 GPU to 3 GPU, but the return is 6 times. From 1.6 requests per second, now we can sustain 10 requests per second, which is a good benefit, right? Now, if our return was anything lesser than 3 or lesser than 3 times, then definitely our investment is not good enough, correct? So that means since we disaggregated the computation between a pre-filled server or a prompt server and the token server, we are achieving higher throughput or we are achieving higher return on investment, right? So again, that simple disaggregation, I mean the idea is simple enough, right? We will have, since the idea is, since prefill and decode has two different computation or two different computation profile, or they have two different characteristics, we will put two different server or different server for through prefill and decode. That's the idea, right? So that simple disaggregation achieves 2x throughput per GPU, which is a good benefit, right? Which is a tremendous benefit. Now let's see some more evaluation. By the way, this is the reference to DistServe. So again, I request you to go over the paper in detail and have more intuition. Okay, so I will repeat myself. I am probably saying this again and again during the course, but we are kind of I am kind of showing you many system optimization in a very high speed, right? I am describing many papers in very quick time. So your job is to not getting limited in this particular topic or in this particular slides, but this particular slides are giving you a good heads up, right? What is this paper about? But you should go and check this paper in detail. Okay, then you will see what is the main catch. I mean, okay, fine. I mean, probably I am giving you the main catch, but you can see that what are the other intuition, how the authors actually implemented it. Is there more theory behind the technique and all those things. So I request you to go over the papers, whatever we are discussing for the duration of the course. Please go over the paper and then understand the paper. So whenever you are going over some paper and you understand the paper, you will see none of the research work is flawless. Okay, but when you understand a research work, when you try to reproduce that research work, then you will see that there are some gap in that research, and if you can identify the gap, if you can solve that gap, that will lead to another research paper, right? Anyway, going back to the topic, let's see the completed request within the latency requirement per second per GPU between VLLM and DistServe. Again, whenever we say completed request within latency requirement, that's the service level objective. In this particular case, the service level objective is latency, maybe the total latency, right? So as you can see that for different algorithm, like they are showing many algorithm. I want to go back. Okay, they are showing for many algorithm like chatbot 1, chatbot 2, chatbot 3, etc. Now you can see that for each of the algorithm, this distributed service, whenever we have disaggregated this prefill phase and the decode phase, this DistServe achieves 2 times to 4.48 times improvement compared to vanilla VLLM. Okay. For chatbot, for different chatbot, the improvement is between 2 to 3.4 times. For code completion, the improvement is 3.2 times. For summarization tasks, the improvement is 4.5 times. So that's a huge improvement, right? Like 4.5 times improvement in throughput is like huge improvement. Like, and again, when we say improvement, remember this is per GPU. It's not for the entire system. Okay, so per GPU we have an improvement of 2 times to 4.48 times with DistServe, right? So again, remember the algorithm is same. They are executing exactly same algorithm. I mean, whenever we say algorithm, I mean the LLM. They are executing exactly the same LLM, but they have done some system optimization. They have optimized how the LLM will be executing on the system. Now, with that tweak, with that optimization itself, they are achieving this much improvement in terms of throughput, and 5.4 times improvement in throughput is huge. I mean, why it is huge? You can think that earlier we were just getting one request per second, or we were serving, let us say, just one request per second, but now with this technique, with this disaggregated service, we can actually sustain, or we can actually serve 5.4 times more request. That is huge benefit, right? So, with that, let us finish this lecture. Thank you very much. In the next lecture, we will talk about fault tolerance in machine learning training. Thank you.